is our second chapter on chemical bonding. We're going to talk about the shapes of molecules and two more bonding theories, valence bond theory, and we'll talk a little bit about molecular orbital theory. If the slides will advance. Okay. So to talk about molecular shape, we're going to use VSEPR theory. So I know the S comes before the E, but we say VSEPR because VSEPR theory is too long, and valence shell electron pair repulsion theory is also too long. So it's just the first letters, valence shell electron pair repulsion theory. And the idea here is that electron groups will repel each other. Okay, this is a very simple model for predicting molecular shapes. So a very important foundation here is understanding what we mean by electron group. We're talking about electron groups, not electron pairs. A lone pair of electrons is one group. A double bond is one group. A single bond is one group. A triple bond is one group. And a single electron is one group. You may say, well, how can it be a group if it's only one? Just deal with it. So what we're doing is we're looking at the electron groups that are on the central atom, and they are repelling each other, and so they're trying to get away from each other. And that's going to help us predict what the molecule looks like. So the preferred geometry will have a maximum separation of electron groups because that will be at an energy minimum. So we'll start with two electron groups. Draw the Lewis structure for beryllium chloride. So there's the Lewis structure. It's violating the octet rule, but remember that beryllium and boron do that sometimes. If we look at the formal charges on chlorine and beryllium, there's 0 on both of them. And so that is the correct Lewis structure. We're going to look at the central atom and ask ourselves, how many electron groups are there? A single bond is one group, and another single bond is a second group, 2 electron groups. Okay? So these electron groups are attached to the central atom, but they don't have to be right next to each other. So this is like you, and this is like your ex, the ex from hell, right? Horrible, horrible, thank you, person. And this is the earth. And so how can you get as far away as possible from that person? Literally go to the other side of the earth. You can't get any farther, right? So that's what these guys are doing. They're getting as far away as possible. Okay? So here we can start looking at the bands. Let's see if I can get them started right. So 2 balloons, right? They'll be opposite of each other because that gives them more space. So this is called a linear geometry because the atoms are in a line. The angle here between those groups would be 180 degrees. Let's look at carbon dioxide. Well, carbon dioxide has 2 double bonds with oxygen, and then the oxygens have lone pairs. We are concerned with how many electron groups are on the central atom. The electron groups on the next atom don't matter. We're looking at what's going on around the carbon. How many electron groups are there? 2. 2 double bonds. Well, how did 2 balloons or 2 people get away from each other? Opposite sides of the planet, right? So these will also be opposite of each other, and this will have a linear geometry. Yes? Yes, we'll get to that. Coming up. Okay, let's look at BF3. So, boron and 3 fluorines. Oops. That's the Lewis structure. Again, violating the octet rule, but boron does that sometimes, and the formal charges are all 0. So we look at the central atom and ask ourselves, well, how many electron groups on the boron? 3, right? Okay, so let's get 3 balloons together. Wrong color. So when I tie a 3rd balloon in here, the original 2 have to get a little closer together to make room for the 3rd one. And what shape does that look like? Triangle? Mm-hmm. Yeah. Ish, yeah. 3-leaf clover, maybe. So this makes a triangle. So this is the triangle that we're thinking about. They will be in a plane because 3 points define a plane, and so no matter how you wiggle these around, they can't occupy more than one plane. It's just not possible. And the angle will be 120. This is called trigonal planar because it's a triangle that's flat, a triangle in a plane. Okay? Let's look at formaldehyde. Here's the Lewis structure for formaldehyde. And this is what you were asking about. Here we have 3 electron groups around the central atom, but the electron groups are not all the same. Here's a double bond and 2 single bonds. So different types of electron groups will exert different amounts of repulsion. This double bond is a little more repulsive than the single bonds. And so, this hydrogen, looking around at what's going on, is like, well, I hate you over here, but I hate you over there more. So I'm willing to get a little bit closer to you if it means I can get further away from that one. So the angles here will not be 120, 120, 120. Now, you do not need to memorize these weird angles. You should be able to tell me that this angle is greater than 120, and this one down here is less than 120. Exactly how much is a detail that's just not important at this point. Okay? So this is also a trigonal planar geometry. It's still a triangle. It's still flat. But the angles are a little bit different. Let's test our understanding. A central atom in a 3-atom molecule forms 2 double bonds and has no lone pairs. What is the geometry of the molecule? Good. So this one is easy to mess up because I don't know about you, but when I see 3 atoms, 3 makes me think of triangles, right? But this is there's a central atom, and it's got 2 electron groups. They're actually, you can draw that very well, 2 double bonds. So here's our atoms, 1, 2, 3. 3 atoms, 2 double bonds. Linear. Mm-hmm. So when we get into 4, things get a little harder to visualize. And here, this is for the YouTube people. I'm making balloons, but you guys don't get to see it. So here's the balloons. So linear geometry, we have 2 things getting away from each other. Trigonal planar geometry, 3 things getting away from each other. So when we're looking at these balloons, the balloon is an electron group. It's not an atom. And where they're tied together, that would be the central atom. So let's look at what happens with 4. So if I take a fourth balloon and pull it into here, the original three are going to have to move a bit to make room for it. So this is not in a plane anymore. This is definitely a very three-dimensional object, right? So we don't run into shapes like that much in everyday life, but that's called a tetrahedron. It has four sides. It also has 4 points, which can be kind of confusing. But each side is a triangle. So there's one side here and one side there, one on the back and one on the bottom. That's a tetrahedron. The prefix tetra means 4. This is 4 electron groups. 4 electron groups makes a tetrahedron. Yeah?
So when you said that the bond angles were different, or depending on what, so if all molecules on the outside are the same or on the central atom, all the bond angles would be the same. Okay.
Yeah.
So, like if those are all the same, they'd all be 109.5.
Right. So if all of these are the same kind of bond to the same type of atom, then you're going to have this ideal tetrahedral geometry where the angles are 109.5. And you would calculate that using some sort of geometry that I don't remember learning about. You should know that number, 109.5. That's the angle for tetrahedrons. Okay. So here is methane. This carbon in the middle, and we have 4 single bonds. We have 4 electron groups. How do 4 balloons get away from each other? They make a tetrahedron. So this is going to make a tetrahedron. And because these are all single bonds to hydrogen, it's going to have all the same angle, 109.5. The Lewis structure, like this, that looks flat, right? Because it is flat. And the angle of separation there is 90 degrees. And that's not what they do. I can make this do it. But it doesn't like it. We are squished. And it will very easily pop back into a tetrahedron. Questions? Okay, what's the geometry of the HCN molecule? Here's the Lewis structure. How many electron groups?
5.
Not 5. 2.
Oh.
I'm very glad you answered. So we're only looking at the central atom, so we're not concerned with the lone pair, right? And this is 3 pairs of electrons, but it's 1 group. Yeah. Because these 3 bonds are between the same 2 atoms, so they can't spread apart from each other because they're stuck on the ends, if that makes any sense. So 2 groups, so what's the structure or geometry? Linear.
How would you determine, like, if you had like a more complex, like how would you determine central atom and if you had?
So if we have more than 1 interior atom, then we look at the geometry at each of them.
Okay. So you
Yeah.
take them individually.
Yep. Yes.
When we first started this,
Mm.
you mentioned that lone pairs count as an electron group.
Mm-hmm.
Are they ever important to?
Yes, they are. Yeah. We're not concerned about this lone pair because it's not on the central atom. We are only looking at electron groups on the central atom. If we have electron groups on the central atom, they very definitely affect the geometry. Okay?
Like that nitrogen is bonded or something, look at that central atom too.
Yeah.
Okay.
Yeah, and we'll do one like that at the end. Okay, so here we have a molecule with 5 electron groups. That's only going to be possible for the somewhat larger elements that can expand their octets. So adding in a fifth balloon. And kind of have to look at it a little bit to kind of figure out what's going on here. Oh, I did a color wrong. Oh well, that's okay. So I meant to make this one a pink balloon also. So this pink one on top is like a little girl ballerina's head. And I guess she's wearing blue tights. These are her legs. And these balloons around the middle are her tutu. See that? Here, this is the one that we're ultimately going to get to. So now we've got the little girl in pink, and this one has a green tutu. And this tutu is fancier, it's bigger, right? So the bond angles here are not all the same. We can set this up so that we have two of these electron groups that are straight across from each other, and we're going to call those the axial positions. Those are like the north and the south pole of the Earth. And then the other groups are around the equator. So these are the equatorial groups. The equatorial groups have a little more space. They have 120 degrees between each of them, and then they have 90 degrees to the axial chlorine. This shape is called trigonal bipyramid because it is a triangular prism stuck to another triangular prism. So we've got a triangle prism on top and a triangle prism on the bottom. So trigonal bipyramid. Not all the angles are the same. And then if we get 6, you guys have to shove over some more. I messed up on the colors, but the string tying is going so much better than it did last night, and I have no idea about it. So I'm going to kind of rearrange these, because they can kind of move around. There we go. So I've got 2 pink ones and 4 blue ones. And now we've got the little girl in her tutu. Okay? But now her tutu has more ruffles in it. It's got 4 instead of 3. So this is called an octahedron. It has 6 points, but it has 8 sides. So sometimes it kind of sticks in your head. It's like, well, there's 6 groups. How can that be an octahedron? Because it makes 8 faces. So octahedron. In an octahedron, all the angles are the same. They're all 90 degrees. Any questions? Let's determine the molecular geometry of carbon tetrachloride. The first thing we have to do is draw the Lewis structure. And I'm not going to talk through this because we've done a bunch of Lewis structures and we are short on time. And I think you're probably tired of listening to me talk about how to make them. So there it is. We want to look at the central atom, the one in the middle, and ask ourselves how many electron groups? 4. 4 electron groups. How do 4 balloons get away from each other? They make a tetrahedron. So this is going to be tetrahedral. Thank you. Any questions? Yeah, that's better. Yes.
Are we going over Bent?
Pardon me?
Are we going over Bent?
Yes. Yep. Bent is coming up.